So how we have started is it's like before diving into the definition and formulas, let us understand what is this deep learning is all about and how these concepts are related with each other. Why there is why there was the evolution of the concepts or evolution of a technology in this particular field. So what we have seen is a deep learning, and then how it got emerged, and then there is what are the differences between the traditional and deep learning. Then, what is the single layer perceptron and what was the XOR problem? So, if I'm able to differentiate between this red and blue dots with the single line, that's a very easy problem, and that can be solved with the single layer neutron or the perceptron. But if we have the dispersion of this red and blue dots over each other and in the circular manner, then it will be, or in the mixed pattern, then it will be difficult for a single layer perceptron or single layer network to differentiate between them. So this problem cannot be solved with this perceptron, and so we require this multi-layer perceptron. That this also we have seen. Then we have seen what is this feed-forward network. So moving from one direction to another direction with the input layer, hidden layer, and output layer. That is done in the feed-forward network. Then why do we require the back propagation? So the network makes wrong predictions, right? So we can manually figure out which knob has turned and how much it has like made the leakage. So like which particularly at which age there is the error and how much error is introduced at those ages. So that is done with the help of the back propagation. The back propagation from the destination node, we reach to the source node again. So you can see here, it is in the opposite direction. The error signal flows in the backward manner. But with this back propagation, we just track in the backward manner, right? This makes the gap. Where is the gap and where is the error? But that error is calculated with the gradient descent. So gradient descent is an optimization method that actually updates the weights according to the error introduced at that particular node. And using this gradient computed by the back propagation, and then moving step by step toward the lowest error. So that's done in the gradient descent. So we have three types of the methods for the gradient descent. We have the batch gradient descent, we have the stochastic gradient descent, and the mini batch gradient descent. So mini batch is the better because it takes the it is a mix of this batch and this SDG method. Correct. Now we'll see this vanishing gradient and why it happens. I hope that, we'll start with this in the today's session. So let's move for this. What is this vanishing gradient? When the back propagation sends the error signal backward through many layers, it gets multiplied by the small number at every layer. So multiplying many small numbers together again and again make the result shrink towards the zero. That's a very simple mathematics. Again, I will say, see, when the back propagation sends the error signal backward through these many layers, it gets multiplied by a small number at every layer. So multiplying many small numbers together and again makes this result shrink towards the zero. So the problem is by the time the error signal reaches the earliest layer, it basically becomes a zero. And those layers stop learning even though the rest of the network trains fine. A very simple analogy is like a telephone game. So you whispered message passes backward, say through the 50 people, and then it gets a little quieter each time. So by the last person, it becomes the silent. Right. So the in the real world, the consequence of this mathematical fact is very serious. So by the time the error signal traveled backward through many layers and finally reaches the earliest layer, the one sitting closest to the input, it has often shrunk to something indistinguishable from zero. So those early layers receive essentially no meaningful correction signal at all. And as a result, they barely learn anything, even while later layers closer to the output continue training just fine. So the clearest way to feel this phenomenon is to imagine a whispered message passing backward, correct? So this is what is the vanishing gradient exactly called as. Now we'll see why these vanishing gradient functions are risky to us. So let's take an overview of it. Naturally, we have this question in our mind. See, why does this the shrinking happens with such a severity, and is it avoidable? So the answer is specifically lies in utilization of activation function. So which activation function we are using in a network, and then because the different function produce very different size derivatives. So two activation functions that dominated the early years of the neural networks, they are the sigmoid and tanh. Now these both functions squash whatever input they receive into the narrow output range. And critically, their derivatives are always small numbers. Correct. So this sigmoid's derivative, for instance, never rises above 0.025, 0.25, no matter what input it receives. So if you multiply these several numbers that are each at most 0.25 together across, say 10 layers, the result becomes vanishingly tiny, and almost immediately this is precise mathematics behind it. Correct. So I hope you have understood. Again, I will repeat. So what I'm trying to say is, as we have see it depends. This shrinking or the vanishing gradient depends upon the which activation function we are using. Correct. So, for example, if we are using the sigmoid activation function, now this sigmoid, whatever input you give, its derivatives tries to squeeze the input up to maximum level of 0.25. So, if we multiply this multiple 0.25 values up to the 0.25 values for say 10 layers, it is going to, of course, going to get a decay to very small number. So, the single mathematical difference matters over here. So if we use the tanh and ReLU, their range is between 0 to 1. So either it becomes a 0 or it reaches to the 1. So repeated multiplication of ones never shrinks the input value. So the single mathematical difference is the why the field needed, and eventually found a genuinely different family of activation functions, which we will be looking into now. So let's see these activation functions. So we have the activation functions as the sigmoid, which is our smooth functions, right? There are some smooth functions also. So having said, just diagnosing the vanishing gradients as a fundamentally an activation function problem. So it makes sense to zoom out and preview the entire solution before examining each piece individually. So activation functions exist to decide whether and how strongly a given neuron fires in response to its input. So without them, no matter how many layers are you stuck, the entire network would mathematically collapse into behaving exactly like one single boring linear network, right? So the history of activation function that follows in the textbook example of this unit has the central theme. So each new function was invented specifically to patch a flaw discovered in the function before it. Right. So sigmoid and tanh, though smooth and easy to interpret, caused the vanishing gradient in deep networks. So ReLU was introduced to fix that specific flaw and succeeded brilliantly. But it introduced an entirely new flaw of its own, which is called as the dying ReLU. Then we have the leaky ReLU was then introduced specifically to patch this dying ReLU problem. Now it is actually fixed with the dying leaky ReLU. So manually choosing the slope remained the limitation in this case. And so finally we have ELU, which was introduced to smooth over that remaining rough edge at the cost of slightly higher computation. So we this is how we have the different functions. So we have the sigmoid. The sigmoid is having its own problem. Then there is a tanh. Then there is a ReLU. ReLU to fix this vanishing gradient. But then this ReLU has the flaw, which is called as a dying ReLU. So then we have the leaky ReLU. This leaky ReLU fixes the problem of dying ReLU. But again, it has its own flaws, and the slope is the limitation in this case. And then so finally we have the ELU, which was introduced to smooth over that remaining rough edge and at the cost of slightly higher computation. So a vivid way to hold this entire progression in our head. And so we will see. exactly what these exactly all these activation functions do. So looking at this relay and how this it is fixing the vanishing gradient problem. So look at this and we'll see that fx is equal to max 0 by x. So if the input is positive, pass it through the unchanged, and if it's negative, output is 0. So the first stop in this journey is ReLU, correct? So shortest form of the rectified linear unit, and its defining rule could hardly be simpler. Just give me some time. There was connection problem. Okay. So coming back to the problem of fixing this problem with the ReLU. So that ReLU is my rectified linear unit, and its defining rule could hardly be very simple. So if input to a neuron is positive, let it pass straight through unchanged, and if the input is negative, output exactly zero. Correct. So this deceptively simple rule turns out to be directly solve the vanishing gradient problem, which was diagnosed. So the reason is very precise. So for every positive input, the derivative, the gradient is always exactly one. So never small fraction like 0.25. So multiplying a long chain of ones together across many layers doesn't shrink anything at all. The error signal survives its entire backward journey fully intact, no matter how many layers it must pass through. So as a welcome bonus, this rule is also extremely cheap to compute, and since it involves nothing more sophisticated than comparing a number to zero. So which is becoming a large part of why ReLU became almost overnight a very popular and the default choice for the deep training networks. Now we'll see about the problem of this ReLU. So the ReLU has the problem of the dying ReLU. Correct. That problem. So please recall the pattern that governs the entire story, right? So every fix introduces its own new flaw. The ReLU is no exception. So consider what happens if during a training, a particular neuron's input gets pushed strongly negative. So perhaps as the side effect of an unusually large weight update, elsewhere in the network, correct? Again, I will repeat. So what happens? I will tell you the exact problem. So during the training, a particular neuron's input get pushed strongly negative. Correct. So from the point onwards, the ReLU's rule guarantees that this neuron will output exactly zero for that input. And that's the critical detail. Correct. Its gradient will always be exactly zero. So gradient of exactly zero means back propagation has absolutely nothing to work with at all, that neuron. So no further backward pass, no matter how many more training steps occur, and can ever change that neuron's weights again. Right. So the neuron has effectively died permanently, and it will contribute nothing to network from that moment forward. The clearest way to picture this is a household light switch that once flipped to off somehow gets glued in that position forever. So no matter how badly the room might need the light later on. So that particular switch can never be turned back. Correct. So this is how this is that this dying ReLU problem is there. So I hope you understand. The obvious question rise for us is like, could we design a version of ReLU that never fully closes, so that even struggling neuron always returns some small chance of recovery? Correct. So the disadvantage of this ReLU was like once it has become a zero, that value, that error cannot be propagated. It will be weighted as zero itself. So we have to find out this problem and saying that, okay, can we have something like which will always have some chance of recovery? And of course, there is a solution for this. So there is a Likirelu which keeps these neurons alive. So let's look into this Likirelu part. So Likirelu answers that exact question with say small but consequential modifications to Relu's rule. So instead of forcing every negative input all the way down to zero, it allows a small fraction of that negative value to pass through. So typically the input multiplied by a tiny number like a 0.01. The practical effect of this small change is significant. So even when a neuron's input is negative, it still carries a small non-negative gradient, which means it is never truly permanently stuck. So there always remain a narrow doorway back to the health during the future turning steps. So this is the best picture as replacing that permanently glued light switch from the previous slide to the dimmer switch instead. Correct. So Likirelu is not a perfect final answer. However, the small negative slope, often written as alpha, is a fixed number that a human engineer must choose manually before training begins. And there is no guarantee that whenever value is chosen will be ideal for every data set. Correct. So every problem the network might encounter. So this residual imperfection, a rigid handpicked constant standing in for something that arguably should not be adopted. Correct. So this is some value. The leaky value is a some value which is to be fixed and which is to be propagated every time. So there is one more solution to this Recchi problem, and that is my ELU. Fine. So ELU, which is the short form of the exponential linear unit, takes Likirelu's core idea one step further by replacing a straight Sharpie angle negative slope with a smooth, gently curving one. Right. So mathematically it is expressed as alpha into bracket e raised to x minus 1. So for the negative input. So while positive inputs continue to pass through the completely unchanged, just as they do in the ReLU and Liquirelu. So why does this smoothness matters in the practice? Because there are two related reasons. The first is a smooth curve, which is the free of the sudden sharp corner found in the leaky ReLU. So tends to make the overall optimization process noticeably more stable, since the network doesn't have to contain with the apparent changes in slope during training. And the second is second is smooth negative curve tends to push the average output of a neurons closer to the zero overall, which has an effect somewhat similar to normalizing the data. And this in turn tends to help the network converge faster and cope more gracefully with the noisy inputs. So that's how the story of this exponential linear unit, that is ELU, comes in the picture. So calculation of exponential function at every single neuron or on every single forward pass is of course expensive than the simple straight line comparison if you do with the ReLU and Licky ReLU. But ELU is the new chapter itself. Fine. So which actually overcomes various problems for this activation function, and then so it has to be used. It is used everywhere. Now moving ahead, and we'll see like why there are optimized and why plain gradient descent is not enough. So let's move ahead and then check like why plain gradient descent is not enough. So look at this. So return to the moment, like to the foggy hillside, which we have seen in our previous slides, correct? So the plane gradient descent taken at a face value has two genuine shortcomings that become especially apparent in the real world training. The first is tendency to zigzag, a picture, a valley that is very steep along its sides, but only gently sloped along its floor. So descending such a valley using nothing but feel the local slope and step downwards. So reasoning causes you to bounce back and forth between the steep walls rather than gliding smoothly along the gentle floor towards the true bottom. Correct. So the second shortcoming is even more fundamental. So I hope the first one is zigzagging. So bouncing the side to side in a valley instead of moving smoothly towards the goal. That is the first limitation. The second limitation is no memory. So every step treated as if it's the very first one. So that's the biggest disadvantage we can say, right? So every first and the most intuitive improvement in this family is the momentum. So it is best pictured as a heavy ball rolling down that same hillside rather than stopping to recompute its direction from the scratch at every single point like the cautious pedestrian. So ball naturally carries forward the momentum of its previous motion, so letting a small bumps and irregularities in the terrain pass by without throwing in seriously of the course, correct? So now let's see the optimizers, various optimizers. So as we have seen, so going back to these optimizers, so with the momentum as our starting point, we now trace the complete evolutionary chain of the optimizers. So once again, we find a similar familiar storytelling, right? So solving one flaw, uncover a new one. So solve that too also. So momentum, as just described, elegantly solves the zigzagging problem by remembering and carrying the forward the direction of the previous updates. So next idea is Adagrad, which tackles a different angle of the problem entirely. It gives each individual weight its own personal and adaptive learning rate, automatically shrinking the rate for the weights that get updated frequently and keeping a large rate for the weights that are updated only rarely. A genuinely useful property. So especially for the sparse data. But Adagrad carries within it the seed of its own failure. So because it keeps accumulating this shrinking effect endlessly without ever forgetting the old updates, its learning rate for any given weight eventually shrinks so close to the zero learning. So we have the RMS prop, which was designed specifically to patch this flaw. So by using a moving average that emphasizes only the recent history of the gradients rather than the network's entire accumulated past. So this simple change prevents the learning rate from endlessly shrinking towards nothing and keeping the training alive for longer. Then finally, we have the ADAM, so which arrives as the natural synthesis of everything learned along this chain, combining the momentums, remember the direction strategy with the RMS props, adapt the rate per the weight strategy into the single optimizer that is simultaneously fast, stable, and adaptive. Again, I will repeat. So Adam optimizers gives the natural synthesis of this what we have learned through this change. So what does it do? It combines the momentums, remember the direction strategy, and RMS props adapt the rate per weight strategy into the single optimizer, so that it's simultaneously fast, stable, and adaptive. So which is exactly why today the Adam has become default starting choice for training the overwhelming majority of the deep learning networks. Right now, we will move to the hyperparameters. So let's move to the hyperparameters. So the hyperparameters, there are different hyperparameters, and we look each one by one. Right. So having now covered how the network learns, like through the backpropagation, gradient descent, and activation function and optimizers. Right. So this is how the network has learned. Right. So now we have to start our story briefly setting to the practical decisions that human must take before training even begins. So known as the hyperparameters. So the first and most structural of this is simply how large should the network be. That is one of the hyperparameter. So choose too few layers or too few neurons per layer. The network end up structurally too simple to capture whatever genuine pattern exists in underlying data. A failure mode called underfitting. correct? And they're recognizable because the network performs poorly even on the very data it was trained, every data which it was trained. So that's my underfitting. Now, if I choose too many layers or too many neurons, on the other hand, the network gains so much raw flexibility that it starts to memorize the system, and even it memorizes the noise of its specific training examples also. So rather than learning genuinely useful general patterns, it failed, right? And this failure is called as overfitting, which is also incidentally raises the risk of running back into the vanish gradient problem discussed earlier. So unfortunately, this is one of our hyperparameter which decides about how large networks should be. And so there is no simple formula that tells us like the correct size in advance. So in practice, the right size is discovered through the patient experimentation, training several candidate architectures and comparing how well each one performs on the data. So it has never seen before and known as the validation state. Right? So this validation set help us in setting the size of network parameter, layer size you can say, and that is one of the hyperparameter. Now moving ahead to the next hyperparameter, which is a learning rate and momentum. So two further hyperparameters that governs the magnitude of each training step, and both were actually the foreshadowed earlier in the stories. So the learning rate eta controls the literal step size taken during gradient descent, as we have seen with the example of the foggy hillside. So set it very high, and the training overshoots the valley floor and becoming unstable or even diverging outright. And if you set it too low, the training crawls forward at painfully slow pace and potentially never reaches a genuine good solution within a practical amount of a time. Right? So that's one of the problem. And then momentum. So it's simply so learning rate. I hope you have understood eta. So too small and too big problem we have seen. Then the momentum, which is another hyperparameter, it simply controls how strongly the network updates carry forward the direction of the previous steps. And if you set it too high, the rolling ball analogy breaks down in the opposite direction. And the ball now carries so much accumulated speed that it overshoots the value floor and oscillates back and forth around the best solution rather than setting into it. So and then setting it too low, the benefit that the momentum originally invented to provide largely disappears, leaving training slow and prone to very zigzag momentum. Correct. So that is again the question like how to set this learning parameter, how to set these hyperparameters, that learning rate and momentum, and that is also we learn through the experiments. Then we have the overfitting problem in detail. So there is a regularization which takes care of this overfitting problem. So you can say a simple analogy for this: a student who memorizes last year's exam answers word by word for word, scores perfectly on the last year's paper, but fail for this year's new question. That is my overfitting. Correct. So network has a million of parameters that they memorize noise, and then they sometimes memorize the noise instead of the learning general patterns. So visible as growing gap between the training accuracy and accuracy on the new data. So with the mechanics of learning now fully covered, the story turns to one final. So that's the regularization. So the phenomenon which is called as overfitting, and that can be overcome with this regularization factor. So on a repeat of that exact same exam, the student would score perfectly. Correct. So if you have a new exam, it is going to fail. So that's my overfitting problem. Right. So to overcome this overfitting, we have the regularization. So regularization techniques we will be looking into. So we have this L1 and L2, and how does it calculate? Correct. So the first family of a curve works by adding a subtle penalty directly into the training process. So penalty is specifically designed to discourage weights from growing unnecessarily large. based on the underlying insight that oversized the weights are usually a telltale signal that the network has become excessively reliant on some specific narrow feature, right, rather than on a broad generalizable pattern. Right. So then we have a particularly interesting consequences of this specific mathematical choice, and that tends to push many weights all the way down to exactly zero. So effectively instructing the network to completely disregard certain input features. So which makes L1 especially useful in the situations where the automatic feature selection is desirable, and the L2 regulation, often also called the weight decay, and takes a gentle approach, penalizing the sum of the squared values of the weights instead. So this produces a smoother, more evenly distributed shrinking effect across all weights, keeping evenly individual weight modest in the size without typically forcing any of them all the way down to the exactly zero. Correct. So in short, L1 tends to produce a sparse network with many weights switched off entirely. And L2 tends to produce a dense network where each weight remains active but kept comfortably small, well balanced. Fine. So then in a regularization, again we have a dropout and drop connect. So let's look at this dropout and drop connect, which is another approach for the overfitting problem. So L1 and L2 attack the problem of overfitting by directly constraining the size of weights to the loss function. A different family of techniques attacks the same problem from an entirely different angle. Right. So by deliberately introducing a randomness during the training itself. So dropout is the most widely used of this technique. At every single training step, please remember what is dropout. At every single training step, a randomly chosen percentage of a neurons, say commonly around 50%, is simply switched off entirely, forcing the remaining neurons to produce a useful result without being able to learn on their now absent neurons. Fine. So the clearest analogy we can say over here is a sports team practicing under an unusual rule. So at every practice session, say half random players are told to sit for the entire session. Correct. So under this rule, what will happen? So every single player over the time is forced to learn to perform competently on their own without heavily depending on the specific teammate. I hope you have understood the analogy. So, meaning that when the real game finally arrives, the entire team plays together. The team as a whole performs far more robustly since no individual player represents a single point of a failure. So that's my dropout strategy. Then there is one more strategy, which is called as a drop connect strategy, which pushes this entire same underlying idea one level deeper. So rather than randomly switching off entire neurons, it randomly switched off individual connection. So specific weighted links between the neurons, creating an even finer grained form of a randomness during the training. So this added granularity can in some cases make the resulting network even more robust than the plain dropout. So which achieves it comes at a real cost because drop connect operates at the level of individual connection rather than the whole neuron. So it's meaningful, more computationally demanding to implement in the practice, right? So this is my dropout and drop connect, which is actually the solution for the overfitting. Now we'll look at this L1 versus L2 versus dropout versus drop connect, regularization parameters, correct? So you can see the comparison. So having now met all four regularization techniques individually, it's worth stepping back and comparing them side by side. So because differences between them reveal the interesting evolutionary logic of their own. So L1 and L2 both act directly on the network's weight by adding a penalty term to the loss function, with L1 tending to produce sparsity, so many weights pushed all the way to zero, while L2 tends to shrink the weight smoothly without eliminating them entirely. Right. Then we have dropout and drop connect. In contrast, act now on the weights directly, but on the network structure during the training, and dropout randomly silencing the entire neurons, and drop connect randomly silencing individual connections between the neurons. with both techniques producing a form of temporary training time sparsity rather than the permanent one. Right? So these are the few differences. And so at the last, let's have the recap of what we have seen. So what we have seen till now is like what is the what is the deep learning network, and then the MLP, feed forward, backpropagation, gradient descent, vanishing gradient, activation function, optimizers, hyperparameter, and regularization. Correct? So when we have the vanishing gradient problem, it is achieved it can be overcome through the better activation function. We have slow unstable descents, so which is overcome through the smarter optimizer, and when there is overfitting, which is overcome with the regularization problem. So deep learning progress is identifying exactly where an idea breaks down and then designing the next idea specifically fits that break. From the single perceptron to our today's deep reversionized and well optimized network. So this is our quick recap of problem and why and fix of it. So single layer network, so can't solve the curve problems, only draws one straight line, and we have the solution of MLP. Then the basic training, there is too many ways to guess manually, so we have the propagation. So this is how, with the quick recap of like we have reached up to the overfitting. I hope this is clear with all of you, and there are no questions now.